Hello everyone, this is Mr. 13 Things, and I am in the middle or the end of a process where I'm evaluating my kids' education, my own education, and the way the world is changing in terms of how we process mathematics and engineering in our world. So at the same time, I'm in the middle of a world where Khan Academy and the Khan Academy Exercise Framework is doing incredibly good things and people aren't paying attention. So I'm going to kind of throw all that together here and leave Smooth Draw 3.2.6 up as I go through this process of talking about really what we should, could, may want to be doing starting around 5th grade or earlier with all these kids that are gaming and learning to fly around weird spaces on their computers, pick off zombies or worse with their Xbox controllers. So I do this showing you, I'm going to let you know I'm running on an iMac about 3 years old. It's got a 2 gigahertz processor and it has 2 gig of RAM. I'm using Windows on that machine, however, and I'm pulling up something called Smooth Draw. What I'm going to do right now is I'm going to go ahead and show you how to set the background to something black. So there, I can hit close here. So my background is white. So I can go to here and I can make it back and hit close. And then I have to say File, New, and then I'm in a file where I've got something that you're used to the screen that Sal Khan uses. So that ability to get the black screen. I will let you know that setting the background, I'm going to now set the background just a little off of pure black. Close, File, New, and then I'm going to set that a little off just so we can differentiate from what I'm doing from the real deal with Sal Khan. All right, so I'm capturing, I'm speaking, and what I'm going to present here is my premise, basically, which is a little bit different than others, is the fact that we are that's not working. I've got to go to the front color here, figure out how to grab green, close, and now I'm going to see if I can grab this tool. I'm using Smooth Draw Edit Cut, right? Because Smooth Draw is free and it's what Sal Khan uses. So we're not going to be like everybody in the world, which is going to say everything that Sal Khan does is perfect, but he does a lot of stuff right. So what I'm saying, my premise here is that the world is 3D, three-dimensional, at least as we understand it, and plus time. And our kids are three-dimensional plus time. From the first time they throw a rock at their kid brother or sister. So we need to go about incorporating that as early as possible. And so I'm going to kind of work backwards to something that three-dimensional plus time generally is the same as, let me call this animation. But not regular old animation, 3D animation. And then go back to the fact that a subset of 3D animation is 2D animation. So as you see things coming out of MIT like Scratch or out of Carnegie Mellon, like Alice, we don't want to forget the fact that all of this occurs because we can deal with 3 dimensions and we have to deal with 3D math. Okay? And so what we're going to look at is how engineers and others deal with 3D math in the most simple form in terms of causing something to translate, rotate, reflect, doing something called transformations. All right, so that's what we're going to be looking at in this and a series of other videos, prezis, transformations, but we're going to be looking at basically 3D transformations, of which, of course, 2D transformations is what we'll start on because they are a subset of 3D transformations. And we should not be, in the world that we are today, forgetting the third dimension. We can keep it at 0 from the start, but we should not be forgetting it from the start. All right, so let's start with something conceptual here, and we're just going to deal with something that a lot of us in engineering use, and that's basically a lot of triangles. Now, there's a reason I think that we deal with triangles when you think about it later, is that triangles, by virtue of their shape, are always going to be convex. In other words, there's no place to hide in a triangle. If you're trying to shoot a laser around a triangle, no matter what the triangle is, it's always going to be a convex shape. All right, now a triangle, if you think about it, is also going to be known as a polygon. Okay, so we're going to call that as a polygon. It's one form of polygon, but a polygon is going to be defined by what we would call then edges, right? 1, 2, 3 edges, and those edges would be defined by points. So you could think about a triangle being defined as by 3 vertexes or 3 points, but it helps a little bit as you get down the road of dealing with this idea of transformations to think about the triangle being enclosed by edges or lines or arcs. Some people would call these arcs if you're dealing in GIS. And then those edges being defined by points. Which means that there is something called a data structure that says, you know, points make up edges and edges make up polygons, which means the fact that polygons are also made up by points. All right, so there's some basic theory underneath this. Here's where it gets to how we present this to our kids. You're just starting with a triangle. We show them a triangle over and over again. We show them a circle. Triangle, because of some of the mathematics of how computers work, we're going to use a little more triangles maybe than we might otherwise have if we were dealing with the pure reality of circles, which is really what the world is a lot about. So the point, I'm going to go ahead and assume that this is on a coordinate plane, and the point right there is going to be 0, 0. But I have to remember right away, 0, 0 is not 0, 0. It is 0, 0, 0. And we have to realize our textbooks, right, are going to be talking about ordered pairs, ordered pairs, ordered pairs. But our textbooks were written before YouTube came into being. So we really want to think about things not in tuples of 2, but tuples of 3. And perhaps one way we can learn to teach kids to deal with that is to let them immediately learn how to do dual notation. And I'll show you how that works in a little bit here. So based on this here, I'm going to go ahead and assume that this is point 1, and we'll look at that and we'll say maybe that is x of 1 and y of minus 1. And this second one there, point here, up here, all right, is going to be obviously perhaps x is 0 and a y of 1. And this third point here is going to be x of minus 1 and y of minus 1. All right, so that's the kind of premise of this. And they're on some place at the moment. We're going to start with them being kind of being defined by an interior point that's at the origin. So what we're going to see in a second here is we're going to start before we end this video with how this notation could be written otherwise. Let me look at this notation of this point here first. Mathematically, you have a tuple of 2 that's called. It's an ordered pair. But when you get into basic computer math or real matrix math, the way you write this is this way. 0, 0 as a column vector, right? And then immediately we want to learn to, no matter if we're using it or not, put the z value there, and you'll see later we'll leave a spot here, but later on we're going to give it a scale of 1. So that will be this point there. This point there is going to be a second column vector, and it would be a 1 in the x, a minus 1, and a 0, and then that 1 scaling vector, scaling number there. And then the third point we have here would be minus 1, 0, and the 1 there. If we train our students to do the dual accounting very early and start doing fun stuff, they'll have a reason to learn their math. Thanks for listening. We're going to move on here. I'm going to keep these to 10 minutes, but I'm going to point an end up here with this statement. As you are collecting or making videos for the web, there's lots of things that are going to take time, but by setting your capture frame to be 1280 by 720, right, you can minimize the post-processing time. So when I'm done with this video here, I'm going to hit stop, save, and then just upload it to YouTube, and I have no post-processing. If you've got great students around or grad students or whatever, they can cut out a lot of the crap, and I'll try to perhaps do that with this one. But what I'll do in the next video, I will pick up this triangle, I will color code it so we can see what we really need to do if we're going to transform a polygon is to transform the edges, and that the way we transform the edges is just to transform the points. And so all we really need is to transform each of these single column vectors, put them back together, and we've transformed our object. So we'll play around a little bit with this video that I'm ending here to see what happens when you transform a square into all kinds of different shapes, but we're going to concentrate on basically just rotation and translation. But the concept of shearing and the like are also going to be basic transformations that we'll use. Okay, so we've got our color set. We've done this in green. I'm going to thank you for listening, and the next video we come to will not spend as much time on the 1280 by 720, the setup of the color and the like. Thanks for listening.